Good morning, students. Welcome to the class again. We were discussing proton NMR spectroscopy. In this class, we will discuss about magnetic anisotropy, splitting of NMR signals and intensities from Pascal triangle, then coupling constants. We were discussing about magnetic anisotropy in the last class. So in cyclophane, this carbon is exactly in the shielded region, so because of that it appears at a very low delta value. Similarly, this CH2 group is exactly in the in the shielded region. So this 10 annuline is aromatic when it is planar. So when it is aromatic, what will happen? These protons are exactly in the shielded region. So because they are in the shielded region, this CH2 will appear at a delta value of minus 0.5 ppm, very low delta value. So whenever we observe some protons in a shielded region, generally they will appear at low delta value than expected. This molecule is called 14 annuline. 14 annuline is again an aromatic system. When we say it is an aromatic system, this methyl group and this methyl group are exactly in the shielded region. They are exactly in the shielded region. So because of that, these two methyl groups, they will appear at a delta value of minus 4.2 ppm. They will appear at a delta value of minus 4.2 ppm. These protons, which are on the periphery of the ring, they will appear at a delta value of 7 to 8 ppm. So this information, we can also take it for aromatic, anti-aromatic. When a compound, something like these annulines, if the inner protons are giving negative delta value and the outer protons are giving positive delta value, then it is aromatic compound. If it is the reverse, that means inner protons are positive value, outer protons are negative value, outer protons appear at a negative delta value, then that is an example for anti-aromatic compound. I'll give you one more example for aromatic compound. It is 18 annuline. In the 18 annuline, we have 12 protons on the periphery of the ring. They are outside the ring. Protons. Because 18 annuline is an aromatic system, these 12 protons are 12 protons. These are outer protons. They appear at a delta value of 8.9 ppm. At the same time, we also have 6 protons in the inside the ring. 6 protons inside the ring. These 6 protons, inner 6 protons, they are exactly in the shielded region, right? So this is exactly shielded region, this is de-shielded region. Because these inner protons are exactly in the shielded region, they appear at a low delta value. Here they appear at a delta value of minus 1.8 ppm. So from this data, we can clearly say that for aromatic compounds, outer protons will appear at a positive delta value, inner protons will appear at a negative delta value. If it is an anti-aromatic compound, then what will happen? Outer protons will appear at negative delta value, inner protons will appear at positive delta value. So from the NMR data, we can predict the aromaticity also. Acetonitrile and chloromethane. We expect that these two are having similar electronegativities. Of course, it is stronger electronegative than chlorine. So we do expect that because chlorine electronegativity is 3, it will have a delta value of 3.05 ppm. So the protons on methyl group, they will appear at a delta value of 3. Now, when we look at the acetonitrile, nitrile group is more electronegative than chlorine, so it is strong withdrawing group. So we do expect a more delta value for methyl groups, methyl protons, right? But the acetonitrile, methyl protons, they appear at a low delta value compared to chloromethane. So here also the reason is simple. The methyl group protons are in shielded region, whereas we don't discuss about shielding, deshielding. Here we purely discuss about electronegativity of chlorine atom. But here, of course, they are attached to a more electronegative atom, but they are in the shielded region. They are in the shielded region. So because of this reason, their delta value will be lower than the expected. So in the case of acetonitrile, the methyl protons appear at 1.97 ppm. I'll give you some more examples like this. So in this molecule, we expect these protons at 1.17 ppm, 1.01 ppm, 0.99 ppm. Because these are all alkane carbons, sp3 hybridized carbons. So we expect these values to be between 1 to 2 or 0.5 to 2. But when you have alpha pinene, the bridged methyl protons, that means protons on this carbon, this appears at a value of 1.27 ppm. So it is in similar, okay, because it is an alkane proton. We do expect this methyl also at the same delta value, more or less, right? But in alpha pinene, it is appeared at a delta value of 0.85 ppm. It is appeared at a value of 0.85 ppm. The reason is that this methyl group also lies in the shielded region. That is why it is giving low delta value than expected. Yeah, this methyl group, allylic methyl group, the delta value will be 1.63 pp. I'll give you one more example, beta pinene. In the case of beta pinene also, we do expect the similar delta values. So this methyl group will appear at a 0.72 ppm. This methyl group will appear at 1.23 ppm. So this methyl which is in the shielded region, they will appear at low delta values. And final example for shielding, deshielding is the phenolic proton, which is next to a carbonyl. Generally, phenolic proton will be observed at a delta value of 4 to 7 ppm. But because this phenol, this OH group is next to acetophenone, the carbonyl, that means it will be in the deshielded region. It will be in the deshielded region. So its delta value is 12.12 ppm. So one reason, of course, phenolic protons will appear from 4 to 7 ppm, but it is also next to a carbonyl. So that means it is present in the deshielded region. So because of that deshielding, it appears at a large delta value than expected. Now we will discuss about the splitting of NMR signals. The number of peaks in a signal is called multiplicity. The number of protons on an adjacent carbon, generally we say alpha carbon, determines the multiplicity. The splitting pattern is explained by two Ni plus 1 rule. For example, we are discussing about only protons. So for protons, I is half. So the final rule 2n half, so it becomes n plus 1 rule, where n is the number of protons on alpha carbon. N is the number of protons on alpha carbon. So this is the basic of splitting, right? Generally in NMR spectroscopy, we don't observe any single peak. For example, we will take a spectra model compound and we will discuss it. In this case, these two carbons are chemically non-equivalent, so these two will give different peaks. Right, but the actual spectrum looks like it gives a triplet and it gives a doublet. This is triplet, this is doublet. So in any NMR spectra, we generally don't observe only single peaks. Generally each peak will be further split into a doublet or triplet, or split into 2 peaks or 3 peaks or 4 peaks or 5 peaks based on the number of protons present on an alpha carbon. So this splitting is generally expected due to the interaction of protons on alpha carbon. So the protons present on alpha carbon will sense their spin. Okay, with their spin they will interact with the spin. So when they interact with their spin, they will split the signal. So the splitting is followed by this rule, n plus 1 rule. If you have one proton on the adjacent alpha carbon, it will be split into one. So I'll write that. So basically the spin-spin coupling of nearby protons result in splitting. The spin-spin coupling of nearby protons result in splitting of the signal. Now, based on n plus 1 rule, I'll give you a table, number of protons on alpha carbon, then multiplicity, how we call it as, and the relative intensities of these peaks. When we have 0 protons on alpha carbon, because based on n plus 1 rule, it will not split the signal. So the signal will appear as a singlet, single peak, that is what is called singlet. This is represented by small s, small letters. We use only small letters. Singlet. Of course, because there is only one peak, relative intensity is 100% or generally in numbers 1. If we have one proton on the alpha carbon, based on the n plus 1 rule, it splits into two peaks. So the two peaks are called doublet. The two peaks are called doublet. Doublet is represented by small d. When we have a doublet, the two peaks will appear with 1:1 ratio. That means the intensities of the two peaks will be same. If we have two alpha protons, then 2 plus 1 3. So the signal will be split into three peaks. The three peaks pattern is called as a triplet. It is denoted by small t. Now the intensities of the three peaks will be 1:2:1. If we have three protons on the alpha carbon, it splits the signal into 3 plus 1, 4 peaks. The 4 peak pattern is called quartet. Quartet. It is represented by small q. The ratio of this quartet is 1:3:3:1. When we have 4 alpha protons, then it splits the signal into 5 peaks. 5 peak pattern is called as quintet. Quintet, the shortcut is QT. Quintet is represented by QT. The ratio of intensities of these peaks will be 1:4:1 plus 3 4, 3 plus 3 6, 3 plus 1 4, and finally 1. If we have 5 alpha protons, it splits the signal into 6 peaks. The 6 peak pattern is called as sextet. The shortcut is SX, small letters SX. Now the ratio of intensities of these peaks will be 1:1 plus 4, 5:4 plus 6, 10:4 plus 6 plus 4, 10:4 plus 1, 5:1. If we have 6 alpha protons, it splits the peak into 7 peaks. The 7 peak pattern is called as septet. The shortcut for septet is SP, small letters. The intensities of these peaks can easily be identified in analogy. So 1 is to 1 plus 5, 6, 5 plus 10, 15, 10 plus 10, 20, 10 plus 5, 15, 5 plus 1, 6, and then 1. If we have 7 alpha protons or more than 7 alpha protons, we generally call it as multiplet. Multiplet. The shortcut is M. We don't represent them. Okay. So based on this table, we can easily predict the splitting in a signal and the relative intensities of all the peaks in the signal. So the general rule for splitting is when we have non-equivalent protons on alpha carbon, they will split each other. If we have equivalent protons on alpha carbon, they never split each other. For example, in ethane, these two methyl protons are equivalent. So we don't observe any splitting here. They will give only one signal. Whereas in chloromethane, these two carbons are non-equivalent carbons. So they will give two signals. When we have non-equivalent protons, then they will split each other. Because this methyl is having 2 alpha protons, it will give a triplet. This methylene carbon is having 3 alpha protons, so it gets quartet. So it is splitting is based on the number of alpha protons. We don't consider how many protons are there on the signal, okay, whether there may be 2 or 3 or 1, it doesn't matter for us, but the splitting is purely based on the alpha protons. Because we have 2 alpha protons, this signal is split into 2 plus 1 3 triplet. Because this carbon is having 3 alpha protons, then these 2 proton signal, it will be split into 3 plus 1 4 quartet. Now, the ratios of intensities of these peaks can be easily determined from Pascal's triangle. How? Say for example, if it is a singlet, only one peak. When we want to divide this singlet into 2 peaks, how we will divide it? We will divide it into 2 peaks with same intensity. 2 peaks with same intensity. So 1 is to 1. When we want to divide this further, we can divide it like this. So this one is divided into 2 peaks with same intensity. This one is also divided into 2 peaks with same intensity. So as a result, what happened? Here it is 1, it is 2, it is 1. So 1 is to 2 is to 1. And again, if you want to go for quartet, just divide them. 2 peaks are there, so we will split them into 2 equal intensities. So altogether here it is only 1, it is 3, it is 3, it is 1. So in such an analogy, we can easily identify the intensities of these peaks. It is 1, 1 plus 3, 4, 3 plus 3, 6, 3 plus 1, 4, and it is 1. 1 is split into 1 plus 1. So this is what is called Pascal's triangle. So you can go for any splitting. We can go for any splitting. 1, 1 plus 4, 5, 4 plus 6, 10, 6 plus 4, 10, 4 plus 1, 5, this is 1. Please take the notes. This is called Pascal's triangle. So using Pascal's triangle, we can easily predict the intensities of all the peaks. So this is 1, 1 plus 5, 6, 5 plus 10, 15, 10 plus 10, 20, 10 plus 5, 15, 5 plus 1, 6, 1. So this is splitting tree or Pascal's triangle.